have a particular input x that you want to know the answer to. The answer is y. It's generated by the model. Well, of course, these average case guarantees in the first bullet tell you nothing about the particular input that you are interested in. And if it's some high stakes, sensitive use case, then average case might not be enough. So our approach is to ask, well, what if the model could additionally generate a proof that y is correct? Okay, so here we're going to be talking about interactive proof systems, formal proofs with formal mathematical guarantees, as opposed to maybe like natural language explanations or interpretability techniques. And where this talk is situated is right between machine learning and trustworthy machine learning in particular, and computer science theory, in particular, computational complexity in this area therein called probabilistic proof systems. And I will tell you about something called self-proving models, which is a formal definition that tries to bridge these two areas together. And whether you consider yourself belonging to the right half or the left half or to neither in this Venn diagram, hopefully, I think the plan is to have maybe 50% of this talk be extremely obvious to you and the other 50% be interesting and new. So don't hesitate to ask questions, because probably in expectation, 50% of the audience has the same question. But yeah, all the definitions, everything should be clear to everybody, not just to the theorists, and experiments should be clear even to the theorists. So this is the plan for today. I'll talk about self-proving models, related literature, theory and experimental results, and some future directions. And the self-proving models results are joint work with Noga and Shafi and Guy Rothblum, who's at Apple. So what are self-proving models? You can have a model, p theta, and theta are the parameters to be optimized, then you have a verification algorithm. And this verification algorithm is trust. It's the source of trust in the system. And formally what this means is that it has this soundness property, meaning that for any input, the verifier rejects all incorrect outputs with very high probability. So this is a randomized verifier. There could be some probability of error, but we can make it as small as we like for all possible inputs. In addition, this verifier should be efficient, more efficient than the prover. And then how things are going to go is that the verifier will interact with the self-proving model in what's called an interactive proof. So there's going to be an input shown to both, and the model will generate an output. Normally we say, okay, I trust this with 99% probability because of my benchmarks, but instead we'll have our algorithm or verifier issue a query or a question and get an answer, and repeat this for r many rounds. And in the end, accept or reject. So this is this rejects incorrect y's. This comes from the final decision that the verifier makes. And the formal definition of self-proving models is, well, I need a few more objects for my formalism. So the first one is I'm going to have a distribution over inputs of interest, x. We have our verifier that is sound, and we have p theta, which I'll just think of as any sequence-to-sequence model. So I don't want to be fidgeting with like this domain, that domain. It's like all possible strings, and it can generate arbitrary strings. And the definition of self-provability with this parameter beta is simply what is the probability over x is drawn from this particular distribution of interest that our prover convinces the verifier. Okay, so this is a probability, and it's over the x's drawn from mu, as well as the verifier's randomness. And since this is a large language model, we're sampling from it kind of autoregressively. So maybe there's some probability in there as well. Okay. There could be many y's that are correct for a particular question x. Right. So this is a property of a prover. If you give me a prover, I can ask, how self-proving is it? Okay, so the honest prover, in the completeness case of classical IPs, has self-provability 1, because it always convinces the verifier if it's perfect completeness.
Well, assuming the distribution is only over yes instances, right?
Yes, true. Yeah. Actually, well, you could think that y is 1 or y is 0 for decision problems, and for search problems, it fits right in. And just to make sure we're all kind of on the same page, because the verifier is sound, then self-provability implies accuracy in the traditional machine learning sense, right? If the prover convinces the verifier often and the verifier is not misled often, then in particular, the prover generated the right answer. So it's a stronger guarantee. All right, any other questions about the definition? I'm going to talk about related work next. So related work actually spans, as you could see already from this morning, this intersection between trustworthy ML or machine learning in general and interactive proofs. It's already a booming area. And I want to tell you about this both to situate our paper and tell you, the context in which it happened, but also just to tell you that you should be excited about this intersection between interactive proofs and ML. There's so many different things people have already done, and it seems to just be happening more and more. So you could learn to prove or learn to verify, safety in Jonah's talk, interpretability in Yining's talk, and other papers as well. And lastly, this thing I call verifier in the loop, which I'll leave as a mystery for now. So other papers that mistakes in the presentation are mine. The papers are solid. OK, so learning to prove, which is kind of our starting point, has been done before for particular proof systems. So Coq, MetaMath, Lean, and more recently, anybody know what paper this is? Alpha geometry, right? So alpha geometry proves to Euclid, the synthetic geometry proof system. And even more recently, alpha proof would have won a silver gold medal in the IMO if it participated, also proving theorems in Lean and using alpha geometry too. But unlike these prior works, we are interested in general in the ability to prove to an arbitrary interactive proof system. Okay, so these are already very powerful results for particular ends, but we are computational complexity theorists, and we want to know what are the limits, what are the possibilities, and what are the limits of doing such an endeavor. Okay, and what we choose to instantiate is like any proof system or any reasonable proof system is this interactive proof system. Interactive proofs are just the general setting of when you have a weak verifier that gets to interact with the powerful but untrusted prover. As we talked a lot about this morning, these are in fact very general because even a polynomial time verifier can decide or can be convinced of problems whose computation might require polynomial space. So far beyond anything that we would think is even reasonable to compute, IPs can capture that. So if we can train models to convince verifiers in IPs, that's going to cover a really big class of computational problems for us. Okay. Now, differently, we can try to learn to verify. And here I want to emphasize that once you have a learned verifier, a deep network or something like that, a priori, you don't have your soundness guarantee anymore. So that's the main difference there. How to get from this to trustworthy machine learning is now a kind of a tricky question because you don't know what your verifier is doing and you don't know whether you should trust its exception. Yeah, but of course there the goal was interpretability or legibility rather than, or in addition to. Yeah, of course, this was introduced by Anil et al. In Prover Verifier Games. And I think, I can say something about this result, especially if you've thought of proof systems a lot. One of the things this paper is doing is it's thinking about NP, so deterministic one-round proof systems. And it's asking, suppose I optimize the prover, or I optimize the verifier, or I optimize both of them at the same time. Game theoretically, so like information theoretically, what's the right order of operations? Should I first try to optimize the verifier to be cheated as least as possible, or should I convince the prover to be convincing the verifier as often as possible? And there, once you cast this as a game, you can ask, is an equilibrium in the game theoretic sense imply complete and sound proof systems? And so depending on the order of operations, the answer is either yes or no. I was really excited when I read that paper because I thought I've not seen anything like this before. Usually I design the verifier and I think of the prover and then I say something.
Is this the version of like Stackelberg equilibrium? Or?
Yeah, so the which equilibrium it is, I'm not like in the game theory area, so I just used this emoji instead. But I just forget, yeah. And more recently, this workshop paper at ICML, whose full version I hope is coming out soon, generalized prover-verifier games to multiple provers, zero-knowledge proofs, so there's more happening in the theory part of things. But as I emphasized, self-proving models prove correctness to a formally sound verifier, so not a learned one, a manually defined one that I trust. And then on the front of safety and alignment, debate systems for AI safety. I took this picture this morning, so we don't need to talk about it even more, but it's very interesting and a lot is happening there. Thanks, Jonah. And the difference is that we are only going to have a single prover, and it's not going to be learned. And no humans either, okay? In the fronts of interpretability, this work is a few years old, published this year. It's thinking of the problem of feature extraction and like useful feature extraction. It casts this as an MA proof system. So for historical reasons, there's Marilyn and Arthur. We're not going to get into it, but it's just think about it as just a single round proof system for us, where the verifier is randomized. And why can we think of feature extraction as a proof system? Well, you can think that the prover is looking at the full input. That's very difficult, a lot of computational power, and it just highlights a small portion of it, of features, and passes this to the verifier, and then the verifier needs to be convinced that this is in fact a bird or it's not a bird. Okay, so this is the setting they explore there, and there's some things can go wrong, but they fix it, and that's also an interesting paper. And of course, prover-verifier games, this was my terrible one slide about it, but fortunately, we just got a really good talk about that, so I'm gonna skip over that as well. And yeah, our goal is kind of trustworthiness rather than interpretability, so we want to guarantee provably correct outputs from our model. We want to quantify how certain we are that our model generated the correct answer, maybe didn't hallucinate, if you want to call things that way. And yeah.
To be a little more concrete, are we talking about getting the models to output lean code or things like that?
Yeah, so in the experiments you'll see here, I use just like an arithmetic problem. So getting the models to answer mathematical questions.
Right, okay, but certainly judge correctness, but then...
well, even for lean...
Okay. So you, I see. So you want a lean proof, which you'll then verify.
No lean. There's actually not going to be for us any natural language, or I don't know if you call lean natural language, but there's going to be a computational, three coloring, but not three coloring. It's going to be some arithmetic problem, the problem of computing the GCD of two integers. Spoiler. And the model is going to have to output the GCD and then prove that it output correctly in the sense of a proof system. So I'll show you a proof system for the GCD. Yeah, there's no lean for us.
But will it be giving a natural language proof?
No. Yeah, we're not going to use natural language. Okay. I think, in fact, this is kind of inherent in my framing, and it's a question I think about a lot. Is ultimately people are interested in problems specified by natural language, but how can you define a sound verifier for natural language? You could say I have a verification procedure, and I think it would work 90% of the time, but for me, it was very important to start out with an algorithm that I write out and I prove that it's sound. Okay. And lastly, I'll just touch on this because I think it's a very exciting work. So this paper is called Fun Search. It's out of DeepMind, and what they did there is their goal was like completely different. It was to solve problems in extremal combinatorics. We are given one input that we care about, X, and we want to generate the optimal Y for X. And the breaking news is that they found state-of-the-art Ys better than what any mathematicians have ever found before for some combinatorics problems. And the reason why, well, I think they said that they use verifiers, and I want to highlight it.
Claims in Fun Search are a bit over.
Yeah, well, it depends on how much you like cap sets, I guess, or...
Yeah.
That's not the point.
Yeah. The point is the verifiers, of course, not the state-of-the-artness or so on. But the reason why is they have this evolutionary procedure which uses systematic verification to filter out results. And I think that if they used better verifiers or more efficient verifiers, they might be able to apply their approach to more difficult problems. Okay, that's all I'll talk about fun search. So hopefully you are now excited about all this work that's happening, and I want to tell you just about this most recent work of ours. Okay, so we'll start out with some theory. Let me remind you of our definition, right? So we have this quantity called the self-provability of a prover. I'm going to think of the prover as an LLM, untrusted, but possibly quite capable, maybe useful, but the verifier is trusted. And I want to optimize, I want to learn the parameters theta of this large language model that maximize its ability to convince the verifier. And I know that if I learn a model that convinces the verifier often, then this model is guaranteed to be correct, and I'll even have like per input guarantee that it's correct. So this is our goal from now on. And I want to tell you our theoretical results about learning self-proving models. Okay, so let's start out with one result. How can we learn self-proving models? Let's fix the distribution and the verifier in the background, and this is going to be the idea. So in interactive proof systems, there's something called the transcript of an interaction. It's simply if we take all the messages exchanged between the prover and the verifier, write them out as one long string, this is called the transcript of this interaction. And the thought is, well, now we have generalist sequence-to-sequence models that appear to be able to solve a lot of sequence-to-sequence problems, not just particular ones you're interested in. So instead of mapping X to Y and being satisfied with that, we're going to map X to the full transcript. We're going to learn how to do that and then extract answering queries from there. And I just want to say, of course, the prover only needs to learn how to generate the answers, not the questions. So okay, this is the idea there. And we basically realize this in a straightforward algorithm that we call transcript learning. And then we have a sample complexity bound on how many samples of accepting transcripts would you need to learn an epsilon self-proving model, or a model that is self-proving up to an error of epsilon. Okay, so let's stare at this for a moment. I'll break down all of these assumptions formally once after I present the algorithm, but under convexity and Lipschitzness assumptions on the problem, given access to accepted transcripts, and this is, I think, the big assumption here, is we assume that we can somehow clone the behavior of some honest prover, so to speak. Given access to accepted transcripts, transcript learning outputs a self-proving model that has error epsilon after this many iterations or this many samples of accepting transcripts. Let's look just at this for a moment. 1 over epsilon squared is, some Lipschitzness bound and some norm bound on the parameters. This just comes from stochastic gradient descent convergence. And the new quantity here is this C. So C is the prover communication complexity. It's a bound on the total number of tokens that the prover needs to send to the verifier in an interaction. And what this is telling me intuitively is that more complex proof systems in which the prover not necessarily needs to do more work, but just needs to communicate more with the verifier are harder to learn. So that kind of makes sense. Like, yes, Vinod, you have a question?
When you get access to accepted transcripts?
Yeah.
What's happening?
You could think maybe you have a doubly efficient interactive, like maybe you can run the honest prover, but you want to run the honest prover like, once in a computationally intensive phase, collect a lot of accepted transcripts, and then learn from it and serve a model forever afterwards.
Honest prover is something that you're trying to learn, right?
Yes, but suppose that computing the honest prover is something that you're okay with doing at some pre-processing phase, but you would rather not do it every time the user, If you had the honest prover downstream, you would never need a model to begin with. I agree. Yeah. So as I show you what, okay, whatever. As I show you what transcript learning does, your question will be answered.
Sorry, what does the convexity mean here?
Yeah, I'll spell this out in a bit. Okay. It's a convexity of some surrogate function that is pretty natural, and I'll show you.
On the transcripts, or?
Yeah, agreement with the transcripts is the short answer, but they'll be spelled out in 2 slides. Aloni?
I should have asked this question a long time ago, but I just realized I was confused.
Oh.
So the guarantee, the 1 minus epsilon, is over the randomness of the instances as well, right?
Yes. Yeah.
So going back to your motivation, I know that on the data distribution, my model is right 99% of the time. Why isn't that the sort of guarantee you're looking for?
Great question. Because it is a worst case, or you know that because you know that the model is right on 99% of the instances drawn from you, but B, you know that whenever the model is wrong, you'll have a verifier that tells you, don't trust this answer. And you can choose whether you want to trust it or not. But does that make sense? So
What if the verifier just always outputs 1?
as in always accepts, then it's not a sound verifier. So we wouldn't have used it to begin with. Assume that, I have a verifier that I have manually proven myself that it is sound. So I manually can control the likelihood, the false positive, or false, false positive. Yeah, this is kind of a nuanced point that's right between in what sense is this a worst case guarantee and not an average case guarantee. So it's pretty important if other people have questions about what's the guarantee. Yeah.
You mentioned soundness of the verifier, but do you have anything about completeness as well? Do you have any assumptions about completeness?
Right. So in general, when we talk about a proof system, we don't really bother talking about proof systems if they aren't both complete and sound. They're trivial. One could always accept, the other could always reject. It's not useful. However, here, it's true that useful verifiers would be complete in addition to being sound, but this is a notion of completeness, if you will. This is kind of a learning notion of completeness. This is a notion of average case completeness with respect to the distribution mu. So suppose that you have a model that's self-proving with probability 99% over x's drawn from mu. It means that it convinces the verifier 99% of the time. So your verifier is non-trivial. So
the error one-sided, essentially, after running the protocol.
I'm making the error one-sided.
But if the verifier accepts, you know you got it.
Yes, yeah. And then the question, and now it's on the prover to convince this verifier, right? So that's what self-provability.
You could have had an interactive proof where the prover didn't always manage to. It could relax completeness in interactive proof. Think about it then.
And so do you assume that you know, the family piece of theta? Right? Because the theorem statement is you output something that does. It's like, I guess it's like proper learning or improper learning. I'm trying to see, is it crucial for you that you know this piece of theta and you actually figure out theta? Because the theorem is theta, you just give a different proof.
Yeah, let's fix a family of p sub theta. And then, yeah.
So you use the assumption that your learning algorithm knows the family of p sub theta and there is some simple parameter theta that you can search.
Yeah, that's that norm bound.
Oh, I see. So this is like within.
Like, think of a p sub theta that's kind of like, it's universal. It can, with huge thetas, it can capture any hypothesis. And then B1 here, the norm bound, or B2, I guess, was how simple that is, and that controls that. Was another question on? Yeah, here we're just gonna have this verifier that says I'm not convinced, but this is a natural extension. I see, you could be like, oh, but here's a certificate that I even knew that the Y was wrong all along. That's really interesting. Was there another one? Okay, so let's move on. I'll tell you about transcript learning. Okay, so step one, Vinod got it, so he's gone. Collect honest transcripts. So let's say I have the honest prover, and I have the problem specification. I'm just going to repeat this for n number of times to collect my samples. I'm just portraying it as being done offline. You could do it online during the algorithm's run if you want. But we sample an X, we simulate this interaction, and now because we have an honest prover, we knew that the verifier would accept. So we'll just write this transcript down in this table, and I'll repeat this n many times to get this data set. And for step two, transcript cloning, I don't need this honest prover anymore. So this is done later when I'm training the model. Okay. And what I'm going to do is simply sequence-to-sequence modeling on this data set. So if you already know what that means, that's fine, but I'm going to spell it out anyways. So for each one of the following transcripts, we're going to optimize theta as following. We'll take each prefix that is going to be fed into this model during the proof. So starting from the input, we know what the correct next token, like what is the next token for y in this data set. So we'll compute the logits of this model, and we'll find out what's the probability that this was, sorry, I should have written here. What's the probability that this is the correct logit? Or sorry, rather, what's the probability that sampling from these logits, we get the correct next token? We'll compute the gradient of this, and we'll continue computing all of these gradients. And finally, we take our gradient step. So theta steps in the direction of the sum of all of the gradients, and we need to normalize by something that we can compute with the forwards pass. So we're happy. Okay, if this is the first time you saw how sequences are generated from sequence-to-sequence models, that was probably a bit fast, but hopefully you're convinced that at least it's something that can be done. Yeah?
Do you also add the probability of the queries to the loss, or are you just ignoring those?
Great question. If you look at the preprint that's online right now, you'll see that we are normalizing by the probability that the queries are sampled, and we realize that if we use a different surrogate function, we don't need them. And that's better because while I can estimate, or while I can compute this probability via the logits, to compute the probability that a query is sampled, I need special access to the verifier that I'd rather not assume I have. But that's a really good question. Yeah. Okay, so this is how sample transcript learning works, and now full specification of the assumptions, all right? So it's the same theorem, except I said assumptions are written above. The first assumption is that this surrogate objective is concave and differentiable. So concave because we're pushing it upwards, but what is this surrogate objective? For a given theta, the objective is to agree with the data set of the transcript. So if I have, we can think of this as kind of a transcript generator that's based on an honest prover. What's the likelihood that if I generate a transcript from my model, it'll agree with the transcript generated by the honest prover? Conditioned on the same randomness of the verifier, just so we don't get different transcripts, you know, because the verifier chose a different question. So this is the objective function that's concave and differentiable. And the proof goes by showing that this objective goes up, and therefore it's a lower bound on the verifiability. So, okay. Next is this communication complexity bound C. And B1 is a Lipschitzness bound on the logits. And then B2 is this norm bound on there exists a hypothesis that is self-provable with error epsilon half. I'm going to reach close to this hypothesis. I'm not going to get this hypothesis, but I'm going to reach close. And what I think is, you know, the real kicker, maybe the real problem with this in some settings is that I assume I have access to a data set of honest transcripts. So let's just talk about this one. And yeah. It has to be from the distribution mu. Yeah. So let's think about how we can get rid of this assumption. So,
with respect to some honest prover for like the one that you assumed has epsilon over 2 thing, or it doesn't matter?
yeah, so in fact, the data set of honest transcript can be collected from different honest provers as long as all the transcripts in the data set satisfy that, one, the inputs were sampled from you, and two, the transcript is correct. I'm happy. Could be different honest provers. Could be like a randomized honest prover if you want. Accepts them. Right.
And you don't count the time to collect those transcripts. You just give a certain number of those honest.
Yeah, the sample complexity here, it's really like the number of transcripts collected. I didn't like account for any of other computational.
So in this number n, is it the number of, like what is it?
Number of transcripts. Yeah, and then everything else is, you know, how complex it is to compute backprop and so on. We decided that was less important to go into, but let's think about how to remove access to the data set of honest transcripts. So we're going to do it with an algorithm called RLVF. together, the computational complexity people and the ML people can figure out what this acronym means. So these letters come from somebody. Not randomized log space. Great. Awesome. Okay. Reinforcement learning, verifier, feedback. Yeah, cool. So reinforcement learning from verifier feedback. We did it. The idea is to simply do rejection sampling on what the model generates to get our accepting transcripts. So this is what the algorithm looks like. We generate a batch of transcripts. We did this already, so we know what that looks like. We got our batch of accepting transcripts. We're going to throw out the rejected transcripts. Okay, so we assume our model has some baseline level of self-provability. And if the baseline level is 30%, then we expect to see 30% accepted transcripts here. And then we just do transcript cloning on this. So we backprop it back through the model. And we repeat this. How many times? I don't know. We don't have a sample complexity theorem for this yet. If you look in the paper, there's like a lemma, which I think is the main thing that you might need to prove this. But since this is basically policy gradient, and showing that policy gradient converges is not as easy as showing that supervised learning works, this has been trickier for us. Experimentally, it's also harder. I'll talk about this later. But this is RLVF, so now you know. Drew.
Hi, so I guess maybe in the experiments this answer will be, or this is a naive question. What is an example of a transcript that I would see if I would use a verifier?
I'll show you. I'll show you in a moment. Experiments. Good question. Other questions about the theory before I move on? Okay. So experiments, we'll do experiments on the greatest common divisor, like a specific arithmetic capability. This is Euclid training a neural net according to Gemini or something. So this is has some context actually for studying transformers. So Francois Charton, really beautiful paper, showed that small transformers can compute the GCD. And why did he do that if GPT-4 can compute much more complicated things? It's because he had an extremely interpretable, like mechanistic understanding of what the transformer is doing in order to compute the GCD, and error analysis at levels that, I don't know, should make everybody envious, like really a full understanding of what are the errors and what is the algorithm that's being learned by the transformer. So this was like rightfully an iClear spotlight, and everybody should check it out. But what we are interested in now is a narrower mission. In addition to computing the GCD, can it also prove that it computed the GCD correctly? So I need to tell you about a proof system for the GCD. And it goes like this. If you've heard about Bezout's theorem tells you that for any two integers, the greatest common divisor of these integers is the only integer linear combination of them that divides both. Okay? It's a lot of words, but I'll just demonstrate by example how the proof system works. The question is, what's the GCD of 92 and 78? The prover says it's 2. And the reason is I'm giving you the coefficients in this integer linear combination above. So negative 11 and 13. And then all the verifier needs to check is, yeah, the GCD divides 92, it divides 78, and it's a linear combination of these integers. X1 and X2, 92 and 78 in this case. So this is the proof system, okay? If you haven't thought about GCDs or Bezout in a while, maybe this was like kind of a lot, but what I want you to take away from this is I can prove that the answer is correct to a verifier using 2 additional integers. Okay, so our proof is going to be 2 additional integers. This is a deterministic 1-round proof system, so we're starting small. Yeah?
I mean, a proof could also just be an execution trace of Euclid's algorithm.
No, because this is cheaper.
This is cheaper. Okay.
Exactly. The verifier must be more efficient than the prover.
I see. Good. Thank you.
So if I need to verify your transcript, we didn't do much.
Thanks.
Great. Yeah. Before I tell you about the experiments, I want to set our scaling expectations appropriately. We've trained LLMs in the Berkeley theory group, okay? So this is attention is all you need, 100 million parameters of GPT. GPT-2, 1 billion parameters. GPT-3 is here, and GPT-4, I tried to think how much like area of the campus would it cover, and I wasted too much time. And this is us there, 6 million parameters, really small. Okay, so this is a model, like no natural language, just sequences. So once again, some GPT-N, and this is a GPT-N-R experiments. GPT-N is trained on all of human knowledge on the internet and will give us utopia or catastrophe if it's regulated or not regulated. But our GPT is trained on, Drew, on these sequences. It's like, I don't know, vocabulary of 60. There's plus sign, there's some integers here, some delimiters. And the goal is to compute the GCD of 2 integers, something that you can write a Python script or do by hand, but proving that the GCD that was computed was correct. And why do we do this? Of course, this is a pretty major limitation if I promise you that this can give you trustworthy machine learning. But we do this, one, because I could do this on 1 GPU, and it didn't take me like a team of engineers. It's just me running these experiments. And 2, it gives us, again, this mechanistic understanding of the training dynamics, like maybe our sample complexity bounds were true up to some stuff that completely explodes when you actually try to run the learning algorithm. So it gives us some grounding that our learning can happen. Yes?
Did you also try just asking GPT or Claude or whatever to output these bazooka proofs?
Yeah, so if you ask ChatGPT to do this, in fact, I conjecture that if you even just show it the code of the verifier and say, convince this verifier, it'll say, sure, here's Python code for the extended Euclidean algorithm. I know it because I read Wikipedia. I'm going to run it. Yeah. You're welcome. Yeah, so that's also why we're happy with these tiny, we'll see curves that actually learn and not just query Python and answer questions. Other questions about the setting, Drew?
Sure. So this.
I will break down the transcript why it's this. I will break down these sequences in a moment. Okay. So bottom line of the experiments is this. If we start from 6 million parameter GPT that Charton already showed can learn, so correctness very high, we can add transcript learning for 100,000 iterations and get to 60% self-provability. Maybe if we keep running it, we will get higher self-provability. But I wanted to find like a practical, why did I do these experiments? I wanted to find an intervention that we couldn't have predicted from theory alone to see how to get this number up to 96%. And, excuse me, this intervention was to add annotations to transcripts. So I'll show you what I mean by annotations. They are intermediate steps in the extended Euclid's algorithm. So here he is back from alpha geometry to the dolly picture everywhere. Okay? So Drew, I will show you how to generate the transcript. Okay? This is the extended Euclidean algorithm. And the only thing I want you to look at is that it's this iterative, or maybe let's think of it as an iterative algorithm, and there are some registers that get updated during the execution of the algorithm. I'm just going to take the intermediate values of these registers up until a certain point and add them as the annotations. So here's a trace table of the execution of extended Euclid on 46 and 39. These are the answers, actually -11 and 13. The GCD is 1. And I'll say, OK, this was the input. And our annotations are going to be the values that were stored by the registers up until a certain cutoff point, because we don't want our context length to grow with the complexity of the instance. And I'll talk about the annotation length in a moment. It's quite important. But what we'll do is we'll take just these highlighted parts. We'll encode them in some base of representation. Let's say we use decimal. As follows. You see like plus 46. This was x0 plus 39. This is x1. Here is the output. These are the sign tokens, the digits and the delimiters. This part is the annotation. We're not going to test the model whether it got the annotation correctly, because that's kind of like a scratch pad. But we will test whether it got the final proof correct. Okay? What you can see here is the learning curves with different depths of annotation. So more annotations help. This is like 60%, and this is 96%. Longer annotations help. And you might say, well, you know what's happening? Depth, so if you look at the instance, you can define its Euclidean depth as the number of iterations that Euclid's algorithm executes. And you can say, well, your algorithm just memorizes exactly the scratchpad you show it, and it cannot do anything other than that. So this is called length. This is the question of length generalization in like sequence-to-sequence models. And this is not the case. So we can see that depth, so if I show it annotations of length 3, it can capture instances of depth 5 and 4 in addition to 3. And the same thing kind of happens up top, but we need to zoom in. Length 4 annotations capture depth 6 instances. So there is length generalization here. It's not just a game of memorizing the annotations. And another result I want to tell you about is, oh, perfect. Another result I want to tell you about is about the effective base of representation. So Charton and his like paper that fully explores like so many aspects of this problem observed that early during training, transformers learn to predict products of divisors of the base B used to represent integers. So base 30 has a bunch of prime factors. That's a good base to use as representation if you're trying to teach your algorithms. So we wanted to see whether the same thing holds for self-provability. And the answer is yes. If I just portray the number of prime factors in the base, it's like statistically significant that it completely predicts the self-provability here. Okay. And I'll end my talk with some future directions. I think this is really the beginning. So RLVF is basically an open question. What are the sample complexity bounds? People who know RL theory better than me maybe can like see this. I'm still working on it. And we want to take this from theory to practice, so we need more complex proof systems like multiple round, randomized verifiers. One might ask just about the problem complexity. We used the GCD because I knew that it'd be not omnipotent when it comes to 6 million, or that 6 million parameter GPT will still struggle with some aspects of this problem if I set it up correctly. But can I scale this up to like interesting problems? And in particular, if I challenge my transformer with a problem that it could only solve correctly, let's say 70% of the times, not 99. Could it be that self-provability as an additional form of supervision actually drives this 70% correctness to like 75% correctness? Because I'm kind of telling the model more about the nature of the problem. Like Bezout coefficients are inherently related to the GCD. I think it'd be interesting, this was a question here earlier, how to adapt this to a more natural setting that's interesting to people, like how can we maybe start from some natural language, reduce it to a computational problem, and then prove the answer on the computational problem. I think one possible direction would be like proof of harmlessness. So if I have a data set of harmful behaviors, this data set could be big, could be computationally infeasible to just test myself that the suggestion of a model won't lead me to harmful behavior, but maybe I task with the model with proving this to me. And larger models, of course. Here's another interesting direction, kind of trying to get a foundation self-proving model. So what does this mean? So far, I've shown you that for any verifier, I can train a model that convinces the verifier, at least in theory. And it'd be interesting to see whether there exists a single model that I could prompt not just with X, but also with the type of verification procedure I'm interested in, maybe in some restricted class. And this p theta would convince all the V's. Okay? And of course, this is really important because we don't expect big LLM company to like train different models for each particular problem at hand. On the theory side, the fundamental theorem of self-provable learning will hopefully find some intrinsic combinatorial dimension in the problem or in the proof system, sorry, that predicts and determines the actual sample complexity and not just this upper bound for stochastic gradient descent that I showed you. And lastly, I think we should just look at existing AI safety frameworks like what Dave was talking about yesterday and Dawn, and try to see how this connects there. I think One of them is Guaranteed Safe AI. They talk about verifiers too. Are we talking about the same verifiers? That's something hopefully I'll figure out this week. Thank you. Preprint is here and the code is there if you want to run experiments yourself on one GPU. So that's it. Thanks. We don't have time for questions, Shafi. They want to eat lunch. It's already, I'll stay here for a bit.
Thank you.